So our first example of a variation of parameters problem is going to be that we're trying to solve y double prime minus 4y prime plus 4y is equal to x plus 1 e to 2x. And in this example, I'm going to be given the fundamental solution set where y double prime minus 4y prime plus 4y is equal to 0. We have the solutions y1 equal to e to 2x, and y2 is equal to x e to 2x. So, to solve for our particular solution, we're going to start out by assuming that yp is equal to u1 y1 plus u2 y2. And for our specific y1 y2, that's going to be u1 e to 2x plus u2 x e to 2x. And then in order to calculate that u1 prime, u2 prime, I do end up needing derivatives of y1, y2. So let's go ahead and get those out of the way. y1 prime is just 2e to 2x. The 2 comes down. And y2 prime needs a product rule. I'm going to get derivative of x is 1 times e to 2x. Plus x times 2e to 2x, or just 1 plus 2x e to 2x when I kind of group everything back up. Then that thing that's at the bottom of all my fractions, I'm going to go ahead and calculate that real quick. That's that y1 prime y2. Nope. Always get it switched. Okay. y1, y2 prime minus y1 prime, y2. My Wronskian. I'm going to go ahead and plug in y1, y2, y1 prime, y2 prime that I just calculated. So y1 is e to 2x times y2 prime is 1 plus 2x e to 2x minus y1 prime is 2e to 2x and y2 is x e to 2x. And I want to make that minus really big, just so that I can tell it's not like a minus 2. Just that there's a subtraction here. I have two terms. But in both terms, I've got this e to 2x times e to 2x. That becomes e to 4x because we can add up what's inside an exponential when we're multiplying them. And then what's left over is all the other stuff. So I had 1 plus 2x from the first term, and then minus 2x from the second term. If factoring out that e to 4x didn't occur to you right away, it would happen once you started distributing and canceling out terms. But these 2 x's cancel out then, and so I'm just left with e to 4x as this complicated denominator of all my fractions. It actually ends up being quite nice. So I'm going to go ahead and try to find u1 prime and u2 prime. u1 is given by minus y2f over y1 y2 prime minus y1 prime y2. And u2 prime is given by y1f over y1 y2 prime minus y1 prime y2. So I can plug in that e to 4x for the denominator, and then I just need my y1, y2, and f. Did I write somewhere earlier what f is? No? Okay. We're just going to note over here, I guess, that f is that x plus 1 e to 2x. It's the right-hand side of the equation. So for u1, we're going to have minus y2, which is x e to 2x, times f, which is x plus 1 e to 2x. All of that over my e to 4x that I just calculated. That e to 2x times e to 2x is e to 4x. We learned that when we were calculating that whole mess up above. So it cancels out with the denominator, and I'm actually just left with minus x times x plus 1, or minus x squared minus x. So everything looked quite complicated, but it is starting to become a little bit simpler. Sorry about that. And then for u2, I'm going to do y1, which was e to 2x, times f, which is x plus 1, e to 2x. All of that divided by e to 4x. So I've got that same cancellation that occurs, and I'm just left with x plus 1. So I know what u1 prime and u2 prime are, and I want to find u1 and u2. So my next step is going to be to integrate those two things. I need to move to the next slide to do it, so please pause if you're still writing. But I've got u1 is the integral of u1 prime dx, and u2 is the integral of u2 prime dx from when I wrote out the next step in those steps to solve from above. So my u1 prime was minus x squared minus x, and I'm integrating that with respect to x. So I'm going to get minus 1/3 x cubed minus 1/2 x squared. And I'm not going to add a constant of integration. We're going to come back at the end of this problem and talk about what happens if we do put a constant of integration here. But like a lot of problems that we've run into in class, it introduces extra constants, and we need to kind of like make sure that we cancel them out, group them with C1, C2 at the end if we do add them. For now, just ignore it, and we'll talk about what happens later. u2 was my integral of x plus 1 dx. That's just going to be 1/2 x squared plus x. Again, ignore plus a constant, but maybe leave a little space if you want to so you can see what happens to it later if you choose to write it in. Then, y sub p was u1 y1 plus u2 y2. I know u1, u2 now, and I was given y1, y2, so I can plug it all in. I've got u1 is minus 1/3 x cubed minus 1/2 x squared. Again, I'm leaving myself a little bit of space to talk about that constant later. E to 2x, and y2 is 1/2 x squared plus x, leaving myself some space times x e to 2x. Yes? Yeah, okay. And I'm going to try to simplify this just a little bit. I know that I have e to 2x on every term, so I'll go ahead and pull that out front. I've got minus 1/3 x cubed minus 1/2 x squared, leaving a little space to talk about later. And then for this term, I'm just going to factor that x, multiply that x in, so this becomes an x cubed and an x squared. So I end up with plus 1/2 x squared plus, x cubed plus x squared, leaving myself a little space for later. And then minus 1/3 plus 1/2 is going to be minus 2 out of 6 plus 3 out of 6, so it's just 1/6, combining those x cubed terms. And then minus 1/2 plus 1 is just 1/2. So that 1 is just 2 over 2, so it becomes 1 over 2. And again, I'm leaving a little bit of space for talking about those constants later. And this is a lot simpler than what I started with. I feel pretty good about it. So I'm going to plug it into my general solution, which is y is equal to c1 y1 plus c2 y2 plus y sub p, which is that u1 y1 plus u2 y2. So in this case, I've got c1 e to 2x plus C2x e to 2x plus this particular solution, e to 2x times 1/6 x cubed plus 1/2 x squared. And that would be the answer to this problem. Once you've got all that written down, I'd like to talk about how we would handle constants of integration here. So suppose I had written like plus a constant when I integrated, which is good practice. Then when I went to yp, I would have plus my constant from u1 here and plus my constant from u2 here. Carrying that further down, when I factored out that e, it would still look like that. And then here, when I multiply that x through, my b would actually become a plus bx. And those wouldn't combine nicely with my other fractions, so I would just leave them the way they were in that last step of yp. Now the reason I wanted to bring this up is because when we get down to this point, you definitely do not want to have plus e to 2xa plus x e to 2xb, which is what would happen if you just carried this term all the way down. You would have 4 unknown constants, c1, c2, a, and b, for a second order equation. So if you had an initial value problem, you wouldn't have enough conditions to solve for all 4 of those things. Instead, you'll note that when you introduce that constant, it's always going to be multiplied by a solution to the differential equation. So a is multiplied by e to 2x, it becomes part of c1, and b is multiplied by x e to 2x, so it becomes part of c2. So same as before, you would end up with c1 e to 2x, it's just a little bit different now, and c2 x e to 2x, a little bit different, and your particular solution that has no unknown constants in it. If you introduce those constants of integration. If you were sloppy and just never added those constants a and b, when you get to the end, nothing would change. But if you do add those constants, make sure you combine them with other constants, same as we have in other sections where we integrate to get to our solution. So with that example out of the way, in our next video, we're going to do another example. So go ahead and hit pause if you need more time. Otherwise, I will move on to the next video.